Now we know that equations of equilibrium cannot be used to find the entire stress state for a problem, as a fully represented stress state has 6 unknowns, and we only have 3 equations of equilibrium. Now let's take a look at constitutive laws and see how can we use the constitutive laws to link stress in the equations to the string. Constitutive laws are used to describe the relationship between stress and strain. Before we dive in further, I wanted to first talk about the classification of material properties, because different materials have different constitutive laws. So we first need to understand the classification of materials. Materials can be classified based on their properties, and there are several properties. First, we can classify materials based on linearity into linear and nonlinear materials. Linearity is defined based on the response and load, such that if the load is directly proportional to the displacement, then the material is linear, otherwise it's nonlinear. Second, we can classify materials based on energy precipitation. We can see that materials are elastic if the energy is independent of the path cycle, or inelastic if it's dependent on the path cycle. Third, using direction and material symmetries, we can further divide materials into isotropic and anisotropic. When the material's response is direction independent, then it's isotropic. When the response is direction dependent, then it's anisotropic. Next, we can divide materials into homogeneous and non-homogeneous. If the material's response is independent of the specimen used in mechanical loading test, then the material is homogeneous, or it is dependent on it, it's non-homogeneous. Lastly, if a material is time dependent, then we can see it's viscous, versus if it's not time dependent, then it's non-viscous. It's important to note that these different criteria are non-mutually exclusive. So we can have a material that falls in multiple categories at once. For example, we can have a material that is linear and elastic, or we can have a material that is non-linear but elastic. In this lecture, we will mainly focus on linear, elastic, isotropic material, because this assumption can really simplify the calculations. And we will also focus on nonlinear elastic materials, which is also called hyperelastic materials. And later on, we might include plastic material as well. So in an isotropic linear elastic material, the response of the material to stress is independent of the chosen coordinate system. In other words, the relationship between the stress strain is independent of the coordinate system. This assumption can really simplify the relationship between the stress and the strain components. The constitutive laws for isotropic linear elastic material has the following form. So epsilon 1,1 is equal to sigma 1,1 over Young's modulus E minus Poisson ratio V times sigma 2,2 over E minus V times the sigma 3 over E. And epsilon 2 is equal to lactive percent ratio times sigma 1 over E plus sigma 2 over E minus percent ratio times sigma 3 over E. And epsilon 3 is equal to lactive percent ratio times sigma 1 over E minus percent ratio times sigma 2 over E plus sigma 3 over E. And 2 times small string tensor epsilon 1, 2 is equal to engineering shear string gamma 1, 2 is equal to 2 times 1 plus percent ratio over E times sigma 1, 2. And 2 times epsilon 1, 3 is equal to engineering shear string gamma 1, 3 is equal to 2 times 1 plus percent ratio over E times sigma 1, 3. And 2 times epsilon 2, 3 is equal to engineering shear string gamma 2, 3 is equal to 2 times 1 plus percent ratio over E times sigma 2, 3. So sometimes we denote G is equal to E over 2 times 1 plus V. It's also called shear modulus. And if we plug in G here, so we can simplify this the shear strings a little bit. We can combine these 6 equations into a more compact form by representing it with a matrix. You will notice that this matrix is symmetric and sparse. So we have many zeros here. And we call this matrix the material property matrix. So given a state of stress, we can find the state of a string. We can also find the inverse of these material properties. So after inverse of this matrix, we get this matrix. So then given string, we can get stress. It's a pure math problem. In many solid mechanics problems, due to the loading and geometry symmetries, we can simplify certain problems to be solved in 2 dimensions rather than 3 dimensions. In these cases, the material property matrix can be reduced from a 6 by 6 matrix. So here we have a 6 by 6 matrix, and they can be reduced to 3 by 3 or 4 by 4 matrix if we account for the symmetries. So we are going to introduce the 3 situations where we will assume that the materials is isotropic linear elastic. So the first situation is one where we have a material that is allowed to freely contract or expand in one direction. And this direction is usually called the cyclic direction. If the loads are only applied in the plane perpendicular to the cyclic direction, then we will only have in-plane stress, sigma 1, 1, sigma 2, 2, sigma 1, 2, and sigma 2, 1. And due to the symmetric, so sigma 1, 2 is equal to sigma 2, 1. So this state of stress is called plane stress because we only have a in-plane stress state. So let's take a look at an example. So here we have a very thin plate. It's a very thin plate. So when I say thin plate, it's because the cyclic direction E3, when compared the cyclic directions E3 to the other two directions, it's very small. Then we don't have any stress on the face with the normal direction of E3. So we don't 1, 3, 2, 3, and sigma 3, 3. These are all zeros. In this situation, the material matrix can be simplified into a 3 by 3 matrix. Now let's take a look. For plane stress, the stress state matrix will be look like this. And then if we plug in the stress state into the constitutive laws for linear isotropic elastic material, we know that sigma 3, 3 is equal to 0. Sigma 1, 3 is equal to 0. Sigma 2, 3 is equal to 0. Then we can cancel the third row, the fifth row, and the sixth row. And if we take a look at the remaining elements in this matrix, we notice that for the last two rows, we have 0 coefficients. So they can be canceled as well. Then this matrix will be simplified like this. So if we move it, move the stress below, and the material property matrix will become this. And similarly, we can find the inverse of this matrix. So the inverse of this matrix is look like this. So given the string, we can find the stress. So, but there is one thing that I needed to mention is that because for this problem, the third direction, which is E3, we allow the third direction to move freely. Then we will have a string along the third direction, which is epsilon 3, 3. It's equal to, so you can find epsilon 3, 3 here, and using these coefficients, you can, after simplification, you can get epsilon 3, 3 is equal to negative percent ratio over E times the sigma 1, 1 plus the sigma 2, 2. The plane string can be used for problems where cyclic dimension is relatively small compared to other directions. For example, like a beam or the teeth of a gear. Now let's talk about plane string. If a material is restrained from contracting or expanding in one direction, which is usually called cyclic direction, and if the loads are applied in the plane perpendicular to the cyclic direction, in this situation, we will have an in-plane string. When we cut the beam in the figure, we can see if we cut it from here, we can see if we apply the load in this plane, and we will not have any string along the third direction. So then epsilon 1, 3 epsilon 2,3 and epsilon 3,3 is equal to 0. So for plane string, we can also, so given a state of a plane string, we can also simplify constitutive laws. So when we plug in epsilon, we know that epsilon 3,3 is equal to 0, epsilon 1,3 is equal to 0, epsilon 2,3 is equal to 0. Then similarly, third column, fifth column, and the sixth column can be cancelled. And because the last row, the last two rows have a 0 coefficients, then it can be cancelled as well. Can be cancelled as well. So if we move the string below, so we will get a new material matrix for plane string. And we can also find the inverse matrix for this matrix. And it has this form. So given stress, we can find a string. And similarly, because we constrain the cyclic direction, so along third direction, we will have a stress, which is sigma 3,3. So sigma 3,3, we can calculate it from here. And after simplification, we get sigma 3,3 is equal to percent ratio times sigma 1,1 plus sigma 2,2. So here we link the sigma 2,2 to sigma 1,1 and sigma 2,2. So you need to use, if you expand here, it's equals to the string times the percent ratio, sigma 1,1 times the percent ratio plus sigma 2,2 percent ratio. And in order to further simplify this to get this equation, you also need to expand sigma 1,1 and sigma 2,2 using this relationship. Now let's take a look at the last situation, axisymmetry. It is used for modeling cylindrical shapes where the loads and boundary conditions are also cylindrical. Then the shear stress along the circumferential direction is 0. So let's take a look at one example. So here we have a cylinder and the load is cylindrical. So if we take this piece here, because it's expanded evenly along the radical direction, then we will not have any stress perpendicular to this plane. So we only have a sigma 3,3 here. So here is sigma 1, sigma 3,1, this is sigma 3,2. Yeah. And if we plug in this stress state in constitutive laws for linear isotropic elastic material, we know that sigma 1,3 is equal to 0, sigma 2,3 is equal to 0. So the last two columns can be cancelled. And we also noticed the last two rows, we have a 0 coefficients. So they can be canceled as well. So we only have this part left. So when we move it down, we can get a new material matrix for Axisymmetry. For Axisymmetry, sorry. Yeah. And we can also find the inverse matrix for this material property matrix. And it has this form. So for this equation, given stress, we can get a string. For this one, given string, we can get stress. So we can also calculate epsilon 3 by using its definition. So if we assume the displacement of this beam after expansion is U1, then epsilon 3 is equal to U1 over its radius.